Previous videos, we looked into how we annotate the images using labelImg, and then how we extracted these bounding box images from the XML files and then saved it into a CSV file. Now subsequently, what we will do is we'll use those information, the bounding box informations on the images, and then extract features from this. And these features we'll be extracting through a special method called the hog, and we'll be explaining this hog method in the subsequent video. But let's look at all those different processes which will happen from now on. Now the first of these processes to build the train and test set from those annotated images. And as I said, we'll be using these hog features extraction techniques for this. And then once these hog features are extracted, then we'll save these features and labels in a HDFI format into disk. So these two will be covered in this specific post. And after that, in the next post, we will build the classifier. Now we'll use those features which we extracted and saved in the disk, and using those features we'll build a classifier and we'll be specifically using an SVM classifier for this. And once we build the classifier, then we get into the inference process, which is typically the image pyramids and sliding windows to detect these objects in the images. And for us, the objects are the potholes on roads. And finally, once we detect these potholes, once we do the object detections, then there's this whole process about optimizing the number of detections which we do, and this is using a process called the non-maximal separations. So the steps 3 to 5 will be implemented in the next post, and this post we will look at how we extract hog features and how and how we save those features into disk. Let's dive in. The feature extractor which we'll be using in our object detector is called hog features. Now hog stands for histogram of oriented gradients. Let's try to understand conceptually what these hog features are. To understand hog features better, let's first understand what are those different parameters which are important in extracting these features. There are 3 important parameters. The first one is pixels per cell, the second one is the orientations, and the third one the cells per block. Let's look at each of them. Now to extract the hog features, the first step is to divide an image into different cells like this. Across the image we divide it by different cells, and then these pixels, and then we define a certain number of pixels per cell. Say for example, if the size of the image is 128 into 128, and we define that the number of pixels per cell would be 4 into 4. So that means, so we'll have 128 divided by 4, that is around 32 into 32. So we'll have 32 different cells like this in both directions. So that's the importance of these pixels per cell. So it just divides these number of pixels which the image holds into different cells. Once these images are split across multiple cells, the next step involves calculating the gradients. Now gradients is nothing but the change in the intensities of light in both the x directions and y directions. So let's say if g of x represent the change in gradient of between pixels in the x directions, and g of y represents the change in gradient in the y directions, then we have to calculate also the total magnitude, which is g is a square root of g of x square plus g of y square. So along with this, we also need to calculate the angle or the orientations in which, or the angle in which the magnitude happens. So if this is g of x and this is g of y. Now this angle also is calculated. So these two things are calculated in the gradient, and the next step is to consolidate this into a histogram. Let's look at how that histogram would look like. So after we calculate the gradients, the magnitude and the angle, the next step involves calculating the histograms. Now to even calculate the histograms or create the histograms, the second parameter, which is the orientations, comes into play. Now we explained earlier that we calculate the angle. Now the total angles, or usually the total range of angles, is between 0 and 180 degrees. So now these 0 to 180 degrees is divided into certain bins, and this bin is called the orientations. Now in this example, let's say the number of orientations which we will have is 9. That is, if you can see, each of those individual bin is of 20 degree angles, and so 180 degrees, the total 180 degrees is divided into 9 different bins of 20 degree angles each. Now each of these vertical bars represent the magnitude which we earlier calculated. So for example, for each pixel within a cell, we look at where these magnitudes and the angles lies, and that's how we get into understanding or creating the total histogram. Now once the histograms are calculated across different cells, what we do is we concatenate different cells into certain blocks. Now let's say we define the cells per block as 2 into 2. That means 2 different cells form a block both in the x directions and the y direction. So this particular these 4 cells form into one block, and these blocks are kind of propagated across the different across these images to extract these histograms across the image, and that's how the feature vectors are formed. Now there are other different processes like your normalizations and so many other processes which are involved, but this is just to see just to give a conceptual idea about how these hog features and what these parameters are and how these parameters are important. Now once these hog features are extracted, now these hog features could be used as for any of the downstream classification jobs, and usually the hog features are always used in conjunction with SVMs. Now what we will see is we will see how we extract these different hog features and how we save it into a HTF file, and then later on we'll see how these features which we saved are used to build a classifier.